Okay, let's talk. So, a little housekeeping first. 2 more weeks to go. It's pretty crazy. We've got really 3 classes and 3 sections left. And I failed on my promise to give you feedback on Saturday, but I'll give you, anybody who's given me any project stuff by the end of today, I'll give you some feedback. I don't know whether that's helpful or not, setting fake deadlines to say, do this, and so you can have some feedback, but maybe it helps. My intention is just to make sure that on Friday, July 31st, you're not scrambling to start working on your project. I can do anything to encourage you, threaten you, push you, incentivize you to get started on the project. If you got ideas about it, let me know, because it's so important to go through a process of thinking about it, getting feedback, working on it again, getting more feedback. It just makes your final product much better. And when you leave it to the end, you're tired, we're all tired, you know, and it's just a time crunch, and then it just generally doesn't turn out as well. So plus you've got the benefit of project one, which I now have said probably 10 times, but the whole point is that you should be able to see where you're going to end up, predict what your final grade is, and predict how you're going to reach your academic goal for this particular class. And that's my acknowledgement that this is not just about learning some cool math stuff that you can apply to the world, but this really has very important consequences for you guys in terms of progressing along the path and what you're here for and what you want to do. And I want to make sure that I help you do that. You know, obviously I could give everybody A's, but I'm not, ethically, I just can't come around to that point of view. So you gotta, you gotta work to earn your grade, and I think any reasonable person would accept that. So yeah, project one is really about that, and project two is really about how do you apply the financial learnings and things that we worked on to something that's personal to you, and really kind of see and articulate, how much the things cost, how much the loans cost, and how do you save money by being more aggressive with your loan, and how much would you save, and what are ways of comparing those things, by time or by dollars or whatever. So those are the big projects that are still kind of floating out there. Of course, exam 3. Oh, I need to send you that list. Let me make a note to myself. That list of topics, but from tests 1 and 2, which appear on exam 3. There's about 10 questions, multiple choice questions. It's only 2 points each, so it's like 20% of that exam is stuff you've already been tested on, quizzed on. I'm not saying that's going to make it easy, but stuff that is not new. Then the other 80% is new stuff, including chapter 13, 14, 15, 16, and 17. And, in some ways, I don't know what's the hardest part. For some people, it's conversions. For other people, it's probability. Like everything we've done in this course, it all boils down to addition, subtraction, multiplication, division, and just knowing when to do what and understanding what kind of problem you're facing. And my job is to try to give you tools to figure out how to do that, how to identify the problem, how to successfully navigate that and get the right answer in a test. And again, part of me feels like that's kind of a dumb thing for us to be focusing on, taking tests, but that's just, so that's the way it is to some extent. Okay, anybody got questions or got one last logbook this week? It's just very easy general feedback for anybody who's taking this course, and you of course would want to include any of your own personal perspective about what is important. I try to pass that on to the next group and give them the wisdom that you have fought for and earned through your commitment. Okay, so let's talk warm-up problems. Find the volume of a concrete slab that's 24 feet by 10 feet by 4 inches. 24 feet by 10 feet by 4 inches. Okay, and I'm going to share my screen. Okay, so what'd you make out of this one?
Now to turn the rest of the feet into inches.
So there's the implied conversion that needs to happen because you have different units. So we would convert 24 feet into inches, that's times 12. We would convert 10 feet into inches, that's times 12. Now, you could have gone the other direction and changed your inches into feet if you wanted. There's no right or wrong in terms of what it is, but if you went all inches, you would have made those two conversions and ended up with those dimensions all in inches. If you went all in feet, it would be 24 feet and 10 feet, and then 4 inches is basically 4/12 of a foot. And that kind of thing causes Excel to go insane, which I always find very annoying. Okay. So after that, what do?
Multiply everything.
Yeah, and this just comes from the basic formula for a rectangular solid. That's part of what's challenging about the problem. There's no picture, it's a description. You've got to kind of wrap your head around what I'm talking about. Concrete slab, you know. Typically that is what happens on the test. There's a description of an object. Maybe it's a container, maybe it's a sign. And then you've got to kind of put together what that looks like and apply the correct formula. So 288 times 120 times 4. This would be what unit?
Inches cubed.
Good. Because we did inches times inches times inches, and that's inches cubed. And then if we did it in feet cubed, it would be 80, which is feet to the third. Okay. And you're welcome to say that as cubic inches or cubic feet. When you calculate those things, don't just do the number. That worries me. I mean, I'll give you partial credit for it, but I want you to say what the units are because that's a part of it. Is acknowledging that it's not just inches anymore, not just feet. Now, if you want a little extra challenge, see if you can convert from one to the other, because that's another thing that you should be able to do, and you will be asked to do for sure, is some kind of squared feet or squared inches converting to something else, square centimeters. So you've got these two numbers, they're equal. You should be able to show that the one is the same as the other. If you can't do that, let me know and I can give you some more feedback and guidance on that. Okay, any questions about the concrete slab problem?
No.
Okay. All right, next problem I think is the dosage problem. The students tend to find this pretty challenging. 15 milligrams per kilograms per day is this piece of information given to us. Patient is 70 pounds and 3 times a day. How much is a dose? Okay, so really kind of taking it to straight into the nursing context. One of the things that can be a little confusing is seeing milligrams and kilograms and thinking to yourself that it's a metric conversion between those two things. but it would be more accurate to say 15 milligrams of medicine for every 1 kilogram of body weight. That's actually the ratio that we're talking about. So even though we're talking about weight, it's the weight of two different things, and therefore there's no conversion between those things. It's a ratio which applies to a person and then tells you how much medicine they should get. The bigger the person, the more medicine they get, right? So if this ratio, so this is really kind of an application of the ratio, the basic ratio concept that we started the class with, right? If it's 15 milligrams of medicine for a kilogram of body weight, then how many milligrams of medicine is it for 2 kilograms of body weight? What would be the equivalent ratio?
Would it be 30?
Right. 30 to 2 is the same as 15 to 1, right? And so on and so forth. Whatever number I have here, 10, I can figure out how many milligrams of medicine I would need. What do I do to this number to get this number?
Multiply.
Multiply
Multiply by
15.
Yeah. So this is not a part of the problem solving process necessarily. I'm just trying to help you understand what's going on between these two numbers, milligrams per kilogram. All of that is complicated by the fact that it's per day. So this happens, every day. We don't need to think about that right now. We can just start with the 70 pounds, convert that into kilograms, right? How many kilograms is that? And then once we have the number of kilograms, then we can convert that into milligrams, kilograms of body weight into milligrams of medicine. And then we can figure out if that's how much medicine they get, that's the daily amount, and we could break it into a dose. So that's kind of the steps that you would need to work through. And some of you maybe already figured that out, and some of you might have looked at that and thought, man, that seems crazy. But that's the process. And we can do it all with fractions if we want, starting with the 70 pounds and putting it over 1. So we can use our conversion process here.
I have a question.
Yeah, go for it.
So you will start off with pounds instead of the 15 milliliters. I mean, why would you start off with pounds?
Well, basically, if you're thinking about this as a conversion process, the 70 pounds is the thing that needs to be converted. I need to take that piece of information and convert it into how much medicine I need to give per dose. So that's one way of thinking about why you start with the pounds. Another way of thinking about why you need to start with pounds is you can't use this ratio until you know how much the person weighs in kilograms. So this is blocking you from being able to move forward. So then naturally the first question is, well, how many kilograms is this person?
Oh, okay.
So if we put pounds on the bottom here, kilograms on the top here, what are the numbers that come out of the formula sheet?
It's 1 pound and you have 0.4536 kilograms.
Okay. So that's the conversion, remember, and then we cross out the pounds and we multiply straight across. That would give us how many kilograms the person is. And then we can use that number to figure out how many milligrams of medicine we're going to need. So this would be 70 times 0.4536. So this is kilograms. So the next step would be to, if we're going to keep using the fraction concept, we're going to bring in this conversion ratio that we wrote down. There we go. So you can see the kilograms is going to cancel there. But you could also just multiply by 15 if you kind of are tracking what's happening here. That's how I take how many kilograms of body weight they have and figure out how many milligrams of medicine they need. So then that leads me to this times 15. And this is the milligrams of medicine for 1 day. And the last conversion would be days to doses. So that's 1 day for 3 doses. And that 8 hours is really an irrelevant number unless they didn't tell you how many doses they need. So basically I need to divide by 3, which again, I'm showing you how the fractions can kind of guide you through the process, but you can also just do this by doing that first conversion and then multiplying by 15 and dividing by 3 if that makes sense to you. I wouldn't try to just memorize those steps without trying to make sense of why we're doing that. Okay, I'm going to bring in my little red pen here and cross things out because that's fun. Pounds, pounds, kilograms, kilograms, days, days. So final answer should be
158.76.
that sounds pretty good. And if possible, you want to avoid rounding to the end of the process. But you know, if you did some rounding in between, like this went to 32, and then that was a little higher, and then this is a little off. From a test perspective, I don't really care. But I don't know how much of a difference that makes in context. You'll find that out when you get to nursing school. Okay, any questions about that dosing problem? Okay, and then the last one was a CO2 problem, which is only really going to make sense if you watch that video that I posted. So we're starting with driving from Indianapolis from Gary, doing a round trip, and the car's getting 26 miles per gallon. So 26 miles per gallon going from Gary to Indy and back. So how many miles is that?
I got 151.6.
Okay, and that's one way?
Yes.
Okay, so then that would be that much 2 ways.
How do you get the 151.6?
Just Google. Because it says find the distance online. That's not how it would be in a test, but finding distances, you know, it's just a matter of putting it into Google and saying, what are the directions from Gary to Indy? And then you'll come up with the distance in Google Maps or something like that. So there's no math there except for multiplying by 2 because it's round trip. Okay, so the process for converting here, and I want to draw attention to the formula sheet, is based on these numbers here in the carbon dioxide emission section. Now, typically there's one of each type of problem. Sometimes they connect them together through a common thread, but we know that we're talking about the 19.8 number because we're talking about gallons. And the way we know we're talking about gallons is because that comes up in the question. Plus, the fact that this is an MPG number, and again, it depends on whether you watch the video or not, but MPG stands for miles per gallon. It's a ratio which indicates that for every gallon of gas that this car uses, you get to go 26 miles. Now that's an average figure. It's way more complicated than that. Sometimes you get better mileage, sometimes you get less mileage, but it's a typical thing for a car is to look at the efficiency of the engine and see how many miles for every gallon. If you are interested in that, knowing your own efficiency, you can start with a Google search, but I've always found that it's more accurate if you just do it yourself, because the real on the ground conditions make a big difference. How inflated are your tires? How do you drive? Are you really aggressive in terms of accelerating and braking, or are you more gentle? And what kind of driving are you doing? So all of that makes a big difference. So if you want to know your own number, let me know and I'll tell you how to do that. Just takes a little bit of math. Okay, so how do I do this problem? Well, again, I think the fraction process that we use can be helpful here. I would start with the miles and convert it into gallons and then convert it into CO2. Okay, so that's the basic structure. And if it's electricity, then it would be kilowatt hours, which you would look at like your watts and your hours, and you would change that into kilowatt hours, and then you would change that into your CO2. I may not use a dash here because it's not division. So in this problem, does anybody feel confident enough to talk about what would come next? What's my conversion factor to get from miles to gallons?
So it would be 26 gallons over 1 mile.
Okay. Just say that out. You said it out loud. Now think about it. 26 gallons for 1 mile. You're using 26 gallons of gas to go 1 mile. Bad news bears. The 26 in front of the miles, right? And the 1 is in front of the gallons. So make sure it stays that way when you use it. But we do need to get, number one, you're right that this is the ratio we care about. And number two, we do need to make sure that if we're using the conversion process, who's going to end up on the bottom?
Miles.
Right. So I put miles down here, I put gallons up here, and then we get the numbers in the right place. So we put 1 gallon here, and we put 26 miles here. So if that's what you meant, that I'm going to have the 1 on the top and the 26 on the bottom, that's right. And then what happens with the next conversion? Because I've gotten rid of my miles then, bam, bam. And the next conversion is and this is where this guy comes in.
So you just have the 19.8 pounds over 1 gallon.
Right. There's a little explanation in the book about where that number comes from. It's basically just some chemistry in the table of elements. You know, the little bit of stoichiometry, which, you know, way more detailed than you are probably interested in. But basically, a gallon produces 20 pounds of carbon dioxide. That may surprise you because a gallon, if you think about picking up a gallon, it doesn't weigh 20 pounds. But the point is that the combustion of the gasoline with the oxygen, those two elements combined produce 19.8 pounds of carbon dioxide, which is a gas. Okay, so that's it. I mean, you just multiply across, bada boom, bada bing. This is a standard application of our conversions. I guess what's different is that these ratios are not truly identity ratios. A gallon is not the same as 26 miles. We're talking about two different things. We're using rates to do the same process. So that would be 303.2 times 19.8 and divided by 26. So that's how many pounds of CO2 are produced in the
Question.
round trip. Yep.
How did you get the 303.2 miles? You multiply. What did you multiply to get that?
Yeah, because 151.6 is one way.
Right.
So we just doubled it.
Okay.
So again, if you haven't watched that video, you want to go back and look at that. I think that there's a lot of value in discussing that and thinking about it in terms of personal choices, saving yourself money by driving less, by using less electricity. But, you know, the amount of work and thinking that you have to kind of put into that to really get somewhere is quite substantial, and the payoff in terms of what you're going to do for the test is quite small. So I've minimized that as a part of what I'm doing in our time together and talking and practicing. But there used to be a project around carbon dioxide emissions, and some people liked it and got stuff out of it in terms of thinking about their own energy consumption and their own driving habits. Okay. Any big questions about conversions? That little part of the last unit we're setting aside and we're moving on to the last part. There's some applications of conversions in individual problems. Maybe this says kilograms, but we want to think about it in pounds or something. But really the rest of the course is kind of its own separate little entity.